Okay, continuation of lesson 3. So still studying refraction, but now we're going to look at something called total internal reflection. So I want you to play around with this simulation right here if you haven't already, and set it up so that the light is starting in a high index material and moving to a low index material. And what I want you to notice is when you make the angle of incidence big enough, the refracted ray disappears. And so when we are moving from high index to low index, there's a special angle of incidence called the critical angle. And we'll look at what this is more in a second. But for right now, just so you know, the critical angle depends on the two media or the two material involved. So say we have light moving from glass to water, the critical angle in that case is 61 degrees, whereas say we have light moving from water to air, in that case, the critical angle is a different number. It's 48.6. And I'm going to use this 48.6 here as an example in a sec, so just keep that number in mind. So when we're moving from high index to low index, there's 3 cases that can happen. First, let's look at case 1, which is regular refraction. So let's say we have water and air. Okay, and we know that the critical angle for water and air is 48.6. I'm just going to write it up here. This is the critical angle. Okay, regular refraction is what you get when the angle of incidence is less than your critical angle. So let's say that this angle of incidence here is something less than 48.6. Maybe it's 30 degrees. In that case, we're still going to get refraction just like we studied yesterday. So the light is going to pass from the water into the air and it will bend. Now let's look at case 2. So this is when we're at the critical angle. So now, okay, assume that this angle right here is exactly 48.6 degrees. And this is still water, and this is still air. Well, when we're at the critical angle, so when the angle of incidence is exactly equal to the critical angle, what will happen is we'll still get refraction. Okay, but when the light refracts, the angle of refraction right here is specifically 90 degrees. And then now we'll look at case 3. Case 3 is what you get when your angle of incidence is bigger than the critical angle. So now, whatever this angle here is, this has to be bigger than 48.6. So this could be 50 degrees or 55 degrees, let's say. And what will happen in this case is that the refracted ray disappears. So now the boundary, which is this solid black line right here, acts like a mirror surface, okay, and the incident ray just gets reflected. And so what you have to know now is that the angle of incidence actually is equal to the angle of reflection. So in the previous diagrams up here, this theta r in case 2 and also in case 1 was angle of refraction because we still had refraction occurring. But now in case 3, there's no refraction anymore, so it's the angle of reflection, and those angles are equal. So this angle here, if the incident angle was 55, the reflected angle would also be 55. Okay, so I've mentioned this already. Total internal reflection only happens when light moves from high index to low index. You can play around with that simulation and just go from low to high and see what happens at all the different angles. You'll notice that internal reflection never actually happens in that case. Okay, example 4. So what is the critical angle for a water and air interface? So let's set this up. Okay, we'll draw the boundary. We have to decide here which is on top and which is on the bottom. So here, we need to remember that critical angle stuff only happens when we're going from high index to low index. It has to be that way. So water has a higher index than air. So I'm going to start the light in the water, and then I'm going to send the light into the air. Okay, So I'll draw in my normal line here. So this dotted line is the normal. And we'll draw the incident ray coming in. Okay, this incident ray, we're looking for the critical angle. So theta 1 here is really the critical angle, and that's what we're looking for. And we know that when we're at the critical angle, the refracted ray will have an angle of refraction of 90 degrees. So now we can actually set this up the same way as we set up our questions from yesterday. So remember, our formula that we're going to use here is called Snell's law, and that's what it looks like on the formula sheet there. So just rearranging, so I have n2 sine theta 2 equals n1 sine theta 1, and we're looking for theta 1. So n2 sine theta 2 over n1 is sine theta 1. So n2 is 1, because the index of refraction for air is always 1, times sine of 90 over n1, which is 1.33. And that gives me 0.75 something. Okay, and so to find theta 1, which is really the critical angle, we're going to do sine inverse of 0.75. And so we get 48.75 degrees, which if we round that to 3 significant digits, we get 48.8 degrees. There we go. Okay, last one. So if light makes an angle of incidence of 60 degrees when traveling from diamond into water, what is the angle of refraction produced? Okay, so it tells us that we're starting in diamond and we're going into water. We'll draw in our normal line. Okay, so angle of incidence is 60 degrees. Okay, so theta 1 here is 60. And then we're going to make a prediction. So in the diamond, the light's going to be traveling slow because the index of refraction is high there. In the water, the light's going to be traveling faster because the index of refraction is lower. So yesterday we learned that when you go from a slow medium to a fast one, you bend away from the normal. So maybe something like that. And this is angle 2. And angle 2 is what we are looking for. Okay, so setting this up again. So we have n1 sine theta 1 equals n2 sine theta 2. So n1 sine theta 1 over n2, that's equal to sine of theta 2. So n1 is 2.42, sine of theta 1, so sine of 60, divided by 1.33. And that gives me 1.57-ish. Now you might remember from math that this isn't allowed. So what I've just calculated there is sine of theta 2. So sine of theta 2 is 1.57. Sine of any angle is never bigger than 1. So I've got something here that's impossible. Or if you forget that, you might try this. You might do theta 2 equals sine inverse of 1.57. Okay, and then your calculator is going to return an error when you try to do that because it's not possible. This error here does not mean that we did something wrong in our math. Our math is actually totally fine. What it means is that refraction is not possible when you use an angle of incidence of 60. Or in other words, 60 degrees is bigger than whatever the critical angle is for diamond and water. And so refraction does not actually happen. And so this refracted ray that I predicted is not actually going to be there. And instead, what's going to happen is that the light, when it hits the boundary between the diamond and the water, is going to reflect. And of course, the angle of reflection is just going to match the angle of incidence.